kind of a max of 3.5 silicon. Again, excellent magnetic properties, and then we control the final properties using our different routings and thicknesses and alloy contents. So there are two main types of electrical steels. We've got grain-oriented electrical steels and non-oriented electrical steels. Now, grain-oriented electrical steels have very strong crystallographic texture, and they're highly anisotropic. So they're really, really good, have really good properties in the rolling direction and not good properties in any other direction. Now, that's okay because they're used for stationary devices. And so you just manufacture the device to have the magnetic field always traveling in the rolling direction. But non-oriented electrical steels, as the name implies, the grains aren't orientated, so they have weak crystallographic texture. And that's because in a motor you have a changing magnetic field from the plane of the sheet, so you don't want it. You want it to be as isotropic as possible. So a little bit about grain-oriented electrical steels. So again, used in stationary applications such as power distribution transformers. They've got very large grains. You can kind of see by the thumb. This is crystallographic grain, and so that provides very good magnetic properties, but not so good strength. But that's okay because it's a stationary device, so it doesn't necessarily need the strength. So we've got two product types at Cleveland-Cliffs. We have the conventional grain-oriented, so that's kind of our lower grade from light Carlite and Carlite. And those are, all the grains are oriented within 5 degrees of the ideal rolling direction. And in the highly grain-oriented space, we've got our TranCore product, where all the grains are oriented within 2 degrees of the ideal rolling direction. When we look at our non-oriented electrical steels, again, rotating applications, motors, generators, much smaller grains because we need the strength. But the much smaller grains than not grain-oriented electrical steel. They're still quite big. And then we've got two main types of non-oriented electrical steel products. We've got our Dymax M grades. And so those are more for the industrial motors. And they range from 0.35 millimeters to 0.635 millimeters in thickness, so the sheet thickness. And we're looking at kind of core losses of 2.9 to 5 watts per kilogram with the 15 hertz induction, 15 Tesla induction at 60 hertz. And then we've got our Motormax grades. So the Motormax grades are targeting and developed for the automotive traction motors. So they are often used at much higher frequencies. So we go to lower thicknesses. We produce 2 to 0.3 millimeters in the HF grades. And we're looking at about 10.5 to 13.3 watts per kilogram with the one Tesla induction 400 hertz core loss, which is kind of a benchmark core loss for this range of products. So, as I said at the beginning, we are a flat-rolled steel producer. So we produce flat-rolled sheet. So the sheet would then go to one of our customers, who would then stamp out laminations and then build a motor stack and build the motor out of it and wind it. So what really is a motor? Now, some of you will probably know this, but like just in case you don't, we have a stator and a rotor. So often in automotive traction motors, we're using permanent magnet motors. So in a permanent magnet motor, kind of see this one single lamination here of the stator and the rotor. And so in a permanent magnet motor, there's holes in a rotor for magnets to sit in. And then in the stator, the stator's wound, so you can kind of see a motor core on the top right-hand side. And it's wound with copper windings. So when a current is applied to these windings, it creates a rotating magnetic field in the stator, which then makes the magnets in the rotor want to rotate as well. And then that's attached to a drive, and it moves the vehicle. So rotor and stator cores, as I said, made up of steel laminations that we produce the flat rolled steel of this. And then the laminations are kind of stamped into stator or rotor geometry. And then for 0.25 millimeter, there's like around 300 laminations in a motor stack typically. And then the laminations are mechanically fastened somehow, glue, bondable coating, laser weld, and then we apply an insulative coating to the sheet so that it stops eddy currents from moving from lamination to lamination. So how do we produce electrical steel at Cleveland Cliffs? So the top outlined in a dotted region, that's kind of a typical routing for your standard carbon steel. This is kind of your automotive structural steel. You're building door rings and parts of the car. So we would produce that out of a blast furnace. You do some refining, you cast it into slabs, then you roll the slabs down in hot rolling. You form a coil, a thick coil. Then you do some processing to that coil. You might roll it down to its final thickness, and you may end up doing a bit of annealing at the end there and package and ship. So this is kind of a standard size routing. But for our non-oriented electrical steel and our grain-oriented, we have a much larger routing and lots of steps. So we'll do our melting, refining, and we'll cast it, and we'll still hot roll it into a coil. But then we have our anneal pickle step. We'll have our first stage cold rolling, and this would be our kind of high-grade non-oriented electrical steel. We'll go through this two-stage routing. So we've got cold roll down to an intermediate, then it would anneal pickle again, cold roll down to the final, then we'll have a annealing line, a coating line, slitting, packaging, ship. And then for the grain-oriented, kind of skipping the melt part now, so going straight to the first coil, the hot band. So we would do all of that, and then we'd come in, do the same anneal pickle, have our two-stage routing with the two-stage cold rolling, but then we'll go on to a decarburization and coating step. We'll go into a box anneal, and that will be to develop the texture that we'd want. And then, like our lower grade, our conventional grain-oriented will go through a scrubbing process, and then a slit and a ship. And then our high grade would go through a further step of thermal vaselining, coating, and in our really high grade, we'll have a laser scribe process as well. And then a slit, package, ship. So as I mentioned in the intro, control of your chemistry is extremely important to get the properties that you want. So if you don't control the chemistry, if you don't control those residuals, you're not going to get the properties that you need. It's a very difficult product to make, both grain-oriented and non-oriented electrical steel. So you can use both an integrated or EAF routing, that would be electric arc furnace, or your classic blast furnace routing would be the integrated routing, where you're getting rocks and turning the rocks into steel. But you need to have the good control over your alloying elements. So what kind of properties are we interested in with electrical steel? So for our non-oriented electrical steel for electric vehicle traction motors, we are primarily interested in core loss and induction. So core loss is a measurement of power loss. It's a measurement of efficiency. So obviously lower core loss, lower power loss is better. And then for our traction grade motor, this is typically measured at 400 hertz, 1 Tesla induction core loss. And that's kind of a benchmark core loss, benchmark frequency for electric motors, or electric vehicle motors. And then for the induction, induction is how easy is it to induce a magnetic flux given an external magnetic field. So the easier it is, the higher the induction, and so the higher value is better. And induction for EV motors is typically measured at 5,000 amps per meter applied field strength, and then you measure the induced field, and that will be called a B50. You can do other ones, but this is really the benchmark for value for the induction. So how do we measure this? Well, it would be very difficult to make a motor for every one of our coils and send those properties of what the stator values would be to our customers. So we do something else. We do an Epstein test instead. And this is just a rough model of what the stator would see. So instead of having a stamped round stator, we would have shear strips and often half in the roll-in direction and half in the transverse direction. And then we'll stack them up alternatively in an Epstein frame, and that frame will have a coil, external coil, and then you'd apply a magnetic field to your strips, and then you'd measure the core loss and induction in your sample. So what is core loss? Now, put simply, and there's a bit of argument around whether these statements are correct, but for the purpose of this talk, we can say total core loss is hysteresis loss plus eddy current loss. So first of all, what is hysteresis loss? Okay, so before we talk about hysteresis loss, we have to talk about magnetic domains. So a magnetic domain, and we see these, if you look at the, unfortunately I don't have a pointer here. Well, I guess I do. Never mind. So if you look at the far right orange magnetic domain picture, we can see that the magnetic domains, you can see the arrows pointing all in different directions. So a magnetic domain is defined by the magnetic moments of all the unpaired electrons in the iron atom are pointing all in the same direction in one domain. And then you go to a next domain and they may be pointing all in another direction. And the next domain, they'll be pointing in another direction. So, but in that region of the domain, they're all pointing in the same direction. So you can see that there will be in the far right middle kind of picture, you can see all the arrows are pointing in different directions. And so you can see, if you look at like one single domain, you would actually measure a magnetic field. But as on a macro scale, they're all canceling out. So you have no induced field. And so when you have the applied field on the x-axis and the induced flux density on the y-axis, and you've got a zero, now you've got a 0B, a zero applied field. When you start having positive H, positive, zero induced